Our next talk is on training data augmentation for detecting adverse drug reactions in user-generated content, to be presented by the first author, Sepide.
Hello, everybody. This is a joint work which I did together with a company called the My Tomorrows in Netherlands. And the topic is about training data augmentation for detecting adverse drug reactions in user-generated content. Monitoring the effect of drug after they have been released into the market is a very important element of drug safety. Adverse drug reactions, which means the harmful reactions caused by taking a medication, can be the fourth leading cause of death in the United States. And the traditional techniques for detecting the adverse drug reaction is they rely on voluntary or mandatory self-reporting of the patients, which will suffer from delays in reporting or under-reporting and data incompleteness. On the other hand, social media data is becoming a very useful source where users and patients try to share their health experiences online. For instance, in this Twitter, we can see that the user writes, "Caved in and had an injection with sumatriptan for my cluster headache. I can only have 2 hours every 24 hours. It makes me dizzy and nauseous." So the user is complaining about being dizzy and nauseous after taking the drug sumatriptan. Or another example can be like, Amanda, "Hey guys, have you ever heard of using Mestiton to stimulate stomach muscle contractions?" This is again about complaining, getting stomach muscle contractions after using Mestiton. Such a user-generated content can provide a valuable insight for monitoring adverse drug reactions in social media from a different point of view. However, extracting this adverse drug reactions from Twitter, for instance, is not a straightforward activity because users report ADRs using very different language styles and terminology. For instance, in professional terms, they might use the word insomnia for when they have sleeping problems, but in a platform like Ask a Patient, they might use like no sleep, or on Twitter, for instance, I can't sleep. So they're using different words or phrases in order to describe one concept. So the existing techniques for automatic adverse drug reactions mainly rely on dictionary matching techniques, which try to match the words in layman health dictionaries to the words in the text, which is on one side very good because no training is required, but on the other side it's of course not able to detect the rare ADRs, so it's only limited to the words in the dictionary. Another technique which is also mainly used is co-occurrence analysis, which they try to expand the dictionary with those that co-occur in the text, which is similar to the dictionary base, and no training is required, but again is limited to the words in the dictionary, and also it can have the problem of semantic drift, which can deviate from the initial meaning after several rounds. And finally, the most popular one is the supervised machine learning techniques or deep learning techniques, which try to train a new ADR detector, which is able to focus on even also rare ADRs. But on the other hand, in order to train such a technique, such a model, you need to have a large amount of training data available. So supervised machine learning techniques, they have shown to perform superiors among the other techniques. However, in order to be able to train them for different platforms, for detecting the ADRs, we need to have large amount of training data, which is very expensive to obtain, especially because usually the domain expert, a medical expert, is required for the annotation. So with the emergence of new informal medical terms, we need to devise new techniques in order to make this process more cost efficiently and more easy. So the main problem that I'm focusing in this paper is the lack of training data. So, for instance, assume that you have a small set of samples and you want to train an ADR detector. Of course, if you just use the small set of samples, it will have a poor performance. And the focus in this paper is to how to augment this training data to have better ADR detectors when limited data is available. So there are some recent work trying to tackle the problem of training data augmentation using, for instance, distance supervision, which try to use the words in the existing knowledge bases, like the medical knowledge base, which is UMLS, and try to match them with the text. And this technique shows decent performance for the common entities, the ones that are mainly used in the text, which exist in the knowledge bases, but again, they don't perform well for the phrases that are not in the knowledge base. Another popular technique is the bootstrapping, which tries to add the most confident classification to the training data in different iterations, which is a very low-cost approach, but again is very limited by the learning capabilities of the classification. And another technique is the embedding-based methods, which try to find these sentences similar to the label training size. And this way we can expand the size of the training data a lot. However, the embedding-based methods, they're limited by the existing sentences available in the corpus. So they cannot generate new sentences. So the focus of our paper is to try to augment the training data using generative models. So having a small set of labeled samples with a large amount of unlabeled samples, we try to first learn the hidden structure of the whole data and using the deep generative models. And then from using that data, we can sample some new sentences from the distribution of that data. And then after having the new sentence, we now need to automatically label that sentence using label propagation from the initial labeled seed. And then by combining the newly generated sentences with the initial labeled ones, we can give it as an input to any kind of sequence tagger to train an automatic ADR detector, for instance, conditional random field, in order to be able to detect new ADRs from the text. So for the sentence generation step, we relied on variational autoencoder, a deep generative model, to generate samples which are similar to the labeled data. Variational autoencoder tries to encode the input into the latent space by modeling the conditional distribution, and then samples samples from these distributions are again encoded into newly sentences. So in this way, we can generate unlimited number of sentences, so it's not limited on the samples existing in the data set. For instance, if we use generative models, if we give as an input, my doctor switched from Celexa to Paxil and Paxil made me feel sick, we can get examples like, my doctor put me on Cymbalta and Cymbalta can help me function, or took my fluoxetine and it was a bit spaced out of my brain. Or another example is like giving input, brought this once putting me to sleep, I need to take a break. It can, for instance, give Viance make me feel like a zombie. So we can generate new samples based on the input labeled training data. But after having new samples, now we need to find a way to automatically annotate this newly samples word by word or phrase by phrase. In order to be able to automatically do this, we rely on measuring and aggregating the semantic relatedness, which we try to find measure the similarity between the words in the new samples with the words in positive terms in the initial labeled samples, which are ADR-related words. And if they are more similar to the positive terms than to the negative terms, then we will consider them as a positive term in the sentence. And after annotating the sentences automatically, now we can give it as an input to any kind of sequence tagger. It's not a problem. It can be BLSTM, RNN, or CRF, or whatever. Here I just use a conditional random field, which is a popular sequence tagger for NLP tasks, which tries to define a set of feature functions and assigns them weights, and then transforms them into probability to detect the output of a label given an entity. And we evaluated our approach by comparing it with other ADR detector, like QMLS, which is a dictionary-based approach, or BLSTM RNN, which is a deep learning-based approach, and CRF is a simple sequence tagger. And then we also wanted to stimulate the effect of the size of training data to see how much we can reduce the training data by changing the training data size and sampling numbers. And finally, we make a comparison to the existing data expansion techniques, like self-training, which is a bootstrapping technique, and Doc2Vec, which is an ensemble-based approach. The data sets that we use one is the social media share tags Twitter, which is a popular data set used for ADR detection. And we also created our own Reddit data set, which we tried to ask a medical expert to annotate some subreddits, health-related subreddits, and we made it publicly available. And for evaluation metric, we use F-score precision recall via approximate matching. And as we can see in the tables, when we compared with other ADR detectors, the dictionary-based approaches, they don't perform well, so they are outperformed by the other techniques, which is, of course, shows that they are not able to detect the terms out of the vocabulary. And as we can see, by adding the variational autoencoder to the sequence tagger, it doesn't matter if it's CRF or it's BLSTM RNN, we can increase the overall performance of the system. And we randomly collected a subset of training data, like 10%, 25%, and so on, and repeated this experiment for 10 times and got an average. And we can see that in all cases, both in Twitter and Reddit, adding variational autoencoder, the data expansion step, it leads to a higher F-score in both data sets. And also increasing the number of artificially generated samples, it can again boost the performance of F-score. So we can see also that the smaller the amount of manually annotated training data, we can see that the effect of adding variational autoencoder is larger. And also, we showed that by using this technique, we can approach the performance of fully supervised approach by just using the 25% of the annotated training data. So we could really reduce the required annotated data which is available. And finally, we compared to different data expansion techniques. The self-training showed that it's not able to increase the recall because it's limited by the outcome of the classifier. And variational autoencoder and the embedding-based method, they show similar performance. However, variational autoencoder can get a higher precision, which is very important because mostly by expanding the training data, we can increase the recall by losing some precision. But in our case, we can still keep the precision high. So as a conclusion, the benefit of our training data generation technique is greater the smaller the manually created training data is. And so we could show that we can reduce the manually training cost by getting the performance as fully supervised by just using 25% of the annotations. However, this is just the initial steps towards automated adverse drug effects analytics on social data. So there are, of course, more research to be done in this area. For instance, linking ADR to the medical ontologies, which makes them useful for more structured analysis for future work. That's it. Thank you. If you have questions.
Hey, great talk. You may have covered this, but what was the average size of length of a Reddit post? Obviously, Twitter has like a 144, 208 characters, but the Reddit post can be
the Reddit post.
Yeah.
They're very much longer than the tweets, of course. It's like 4 to 5 sentences. I don't know the words. I have it in the paper, the average number of words. And the variational autoencoder performs better on shorter sentences. So, yeah, that's
Thanks.
Also shown in the paper.
Got time for one more question? Yep.
Hi. Have you tried to combine your method with self-training and see if doing both would improve?
Yes, I tried it and no improvement.
Any guesses why?
Yeah, because self-training, it's very limited to the output of the classifier, so really it didn't bring up the recall. So, yeah.
Okay, let's thank our speaker.